This is my first video lesson for Unit 12, Equilibrium. In this lesson, we'll be describing equilibrium. Go to page 2 in the class packet. You can download the class packet on my website. Motivation. Take a moment to describe what's happening in this GIF. Are things changing? Is there a net change? This is an analogy of equilibrium. Learning target. At the end of the lesson, I'll be able to describe equilibrium in physical and chemical changes. Home will be number 1, which will be a junipod based off this lesson. Equilibrium is when both the forward and reverse reactions occur at the same rate in a reversible reaction. A reversible reaction is when the forward and reverse reaction occur at the same time. Let's look at an example of a reversible reaction. In this reaction, hydrogen is reacting with oxygen to form water. This is the forward reaction. This reaction can also go backwards. Water can decompose back into oxygen and hydrogen. This is the reverse reaction. So this reaction is reversible. If the forward reaction is exothermic, the reverse reaction must be endothermic. A reversible reaction is represented by an arrow that points forward and backwards. There are many variations of this arrow. If you see this arrow in a chemical equation, it means the reaction is reversible. The opposite is the irreversible reaction, a reaction in which the reactants convert to products and where the products cannot convert back into reactants. In a chemical equation, the arrow is only pointing in one direction. An example of an irreversible reaction is baking a cake. When the ingredients are mixed together and undergo a chemical reaction to become a cake, the cake cannot go back to become the ingredients. When a reaction is at equilibrium, it is not necessarily the same concentrations of reactants and products. It might be the same, but not always the case. At equilibrium, there is a mixture of reactants and products. The concentrations of the reactants and products are constant. Equilibrium can exist under these conditions: constant temperature, and closed system. Learning check number 1. What occurs when a reaction reaches equilibrium? Pause the video and resume as completed. The answer is choice 3. The rate of the forward reaction is equal to the rate of the reverse reaction. Learning check number 2. When a reversible reaction is at equilibrium, the concentrations of the products and the concentrations of the reactants must be what? Pause the video and resume as completed. The answer is choice 3, constant. There's two types of equilibrium, static and dynamic. Static equilibrium is when the object is not moving and all the forces are balanced. You will learn this in physics. Dynamic equilibrium is when the forward and reverse processes are happening continuously, but there is no net change. Here are some GIFs of dynamic equilibrium. This unit will be focusing on dynamic equilibrium. Here's a summary of what we talked about so far. In order for something to be at equilibrium, it must be a closed system and the temperature must be constant. In addition, the forward rate must be equal to the reverse rate. The concentrations of the reactants and products is constant. In summary, things are changing, but there is no net change in the system. Learning check number 3. The diagram below shows a bottle containing NH3 gas dissolved in water. How can equilibrium be reached? Pause the video and resume as completed. The answer is choice 4, because the system must be closed. Now we're going to look at different types of dynamic equilibrium. The first one is the phase equilibrium, which occurs during a phase change. On the heating curve, equilibrium will exist at the flat parts because that's during a phase change. Here's an example. During boiling, water in a liquid state becomes water in a gas state. If the lid is on during boiling, phase equilibrium will exist, as you can see in this GIF. In the previous unit, we talked about different types of solutions, unsaturated solutions, and saturated solutions. Which of these solutions has equilibrium? That would be the saturated solution. This is known as solution equilibrium, and it only occurs in saturated solutions. So here I have a saturated solution of NaCl. As you can see, the rate of dissolving is equal to the rate of crystallization. The next type is chemical equilibrium, which is present in a reversible chemical reaction. The forward rate is equal to the reverse rate. The amount of reactants and products are constant, not necessarily the same concentrations of reactants and products. Here's a GIF to show chemical equilibrium. The rate of forming products is equal to the rate of forming reactants. The last type is concentration equilibrium. Through a semi-permeable barrier, the solvent from a low concentration moves to a high concentration to dilute it till the concentrations are equal. Here's a GIF to show this. Learning check number 4. Which equation represents chemical equilibrium? Pause the video and resume as completed. The answer is choice 2 because that's showing a chemical change. Learning check number 5. Based on reference table G, which amount of compound dissolved in 100 grams of water at the stated temperature represents a system at equilibrium? Pause the video and resume as completed. So you're looking for a saturated solution, which is on the line. The answer is choice 2. Learning check number 6. The solid and liquid phases of water can exist in a state of equilibrium at 1 atmosphere of pressure and a temperature of what? Pause the video and resume as completed. Equilibrium exists during a phase change. The phase change between a solid and a liquid is melting. Water melts at 0 degrees Celsius, so the answer is choice 1. Here's a concept map to summarize what we talked about. On page 3 in the class packet, there's a data table of the concentrations of these substances. Take a moment to graph these substances onto this graph. The curves will show the concentration of each of these substances before and after the reaction reached equilibrium. Here are the graphs. So as you can see, in the beginning, we only had reactants H2 and N2. As the reaction progressed, NH3, which is the product, is formed. As NH3 is being formed, the reactant's concentration decreases. Eventually, the reactants and the product concentration is constant. Once they are constant, equilibrium is reached. Based on the chemical equation and the graph, we'll be answering these 3 questions. The forward reaction is exothermic. The reverse reaction is endothermic, because the energy is on the product side of the chemical equation. How many seconds does it take for this reaction to reach equilibrium? By looking at the graph, it is 5 seconds. Are the reactants and products at equal concentration at equilibrium? By looking at the graph, the answer is no. The concentrations are constant, but they're not equal. Let's look at more examples of graphs of equilibrium. Here we have 2 graphs showing this reaction at equilibrium. A is the reactant and B is the product. What is the difference between these 2 graphs? If you notice, the difference is the y-axis. The graph on the left, the y-axis is concentration. The graph on the right, it is rate. Are they telling the same story? The answer is yes. The graph on the left tells us when equilibrium is achieved, the concentrations of A and B are constant. The graph on the right tells us that the forward rate and the reverse rate are equal at equilibrium. Now let's look at the effect of catalyst on equilibrium. A scientist decides to test the effect of platinum catalyst on this reaction, which we graphed already. He sets up a new experiment with identical conditions, except a solid platinum catalyst is added. The concentration of the products and reactants is the same as before. However, the equilibrium was reached in 2 seconds. Explain how a catalyst affects the reversible reactions in terms of equilibrium. From the passage, adding a catalyst caused the equilibrium to be reached in 2 seconds. From the graph, without the catalyst, equilibrium was reached in 5 seconds. Therefore, adding a catalyst speeds up both the forward and reverse rate to the same extent. In addition, adding a catalyst does not affect the equilibrium concentration, which is the same as before. Here's the effect of catalyst on graphs of equilibrium. Notice with a catalyst, equilibrium was reached faster. Learning check number 7. Given the reaction at equilibrium, The addition of a catalyst will do what? Pause the video and resume as completed. The answer is choice 3. Increase the rate of the forward and reverse reactions equally. This concludes the video lesson. Remember to do the Junipod homework.